Okay, so we've got our reactor, we've got particles in that reactor, and we need to estimate the reaction rate that's actually happening inside this reactor. We do have a balance on that reactor, which we can write as dCA dt is Ca in minus Ca over tau minus RAV. So we'd like to determine the reaction rate from that. We determined from the last one that RA is equal to RA double dash times SA times MCAT divided by the reactor volume. So RA double dashed we have as being the kinetic rate constant Ks times the concentration of A. But that concentration of A is actually the average concentration across the particle. So if we have our particle here, there exists some concentration of A, in fact a concentration profile of A, right, as A is diffusing into the pores of that reactor. As it diffuses in, A is being consumed, right? Remember the pore, if we look at a pore, let's follow that pore. Let's say that's what the pore looks like. So you've got catalyst sites all along the walls of this pore. So as A is diffusing in to this pore, it's reacting with these sites here, and so A gets depleted as it diffuses into that pore. So your concentration of A is diminishing as we look further into the particle, and that complicates our attempt to estimate that reaction rate, right? This rate here, this is the area-based rate, and that rate is going to be different for every point along this pore. So what we need to do, what we actually want is the overall reaction rate for the whole reactor. So we'll start out looking at a single particle, and we recognize that even though the rate is different right across this pore here, there must exist some average reaction rate across this pore, and likewise there must exist some average reaction rate across that whole reactor. And that average reaction rate must be what we'd get if we took the kinetic rate constant and multiplied it with the average concentration across that particle. So we'd like that average concentration, recognizing that there will exist some surface concentration of A, so let's call that CAS, and that surface concentration is still not the same as the bulk concentration of A. Right, that's the concentration in the fluid that's flowing around that reactor. It's not the concentration by the particles. So that's the bulk fluid concentration. That's still not necessarily the concentration on the surface of the particles, because remember, there's your external mass transfer limitation that may cause the concentration here to be different to the concentration in the bulk. So in the bulk fluid, there is the Ca, right? That concentration is what we have in the overall mass balance. So this concentration may be different to the concentration on the surface, just by virtue of the fact that A is being consumed inside the particle. So there will be a lower concentration of A here, and then if it does take some time to diffuse from the bulk fluid towards the particle, then that concentration gradient exists. So there is possibly some external transfer limitation there. So let's try and estimate that. First of all, on the surface itself, there exists this concentration here, CAS. So we can say there exists a surface reaction rate for A, and that reaction rate at equilibrium must be the same as the transfer rate of A across that film. So let's call the transfer rate across that film JA, and the reaction rate RAS on that surface, that must be the kinetic rate constant, right, same as that, the kinetic rate constant multiplied with the concentration on the surface. So let's let CAS be that concentration. Then the mass transfer rate across the external film here, that's nothing but Kc, the mass transfer coefficient in the film, multiplied with the concentration difference across that. So that's Ca minus Cas. Right, and that gives us an equation which we can use to solve for CAS. So we can say CAS is equal to Kc over Kc plus Ks times Ca. Right, so if you just group out CAS, you'll get that expression. So this tells us how we can relate the concentration of A on the surface of that particle with the concentration of A in the bulk there. Right, so that's just dependent on the mass transfer coefficient, that applies here, and the surface reaction rate constant there. So that's the first correction we have to do. We have to get from the bulk concentration to the surface of that particle that's there. And now that we have that, we hope to be able to estimate some average concentration in the particle.